This conference will now be recorded.
Good morning, students. In today's class, we are going to discuss about transformation ratio and what is the importance of transformation ratio. What are the parameters are involving in that equation? So that is the topic we are going to discuss in today's class. So before going to that, the transformation ratio, the equation should came from that EMF equation. So first of all, I will tell you that how we can derive the EMF equation, and then we go for that transformation ratio. So already we discussed that the derivation of EMF equation in the single phase transformer, right? So just I'm going to write again. The EMF equation for primary winding we can write E1 is equals to 4 point. So E1 is equals to 4.444 F pi m and N1. This is the EMF equation that represents that primary winding. So here F is the frequency and pi m is the maximum flux and N1 is the number of turns. So the same equation we can represent like this 4.44 F. Instead of pi m we can write Bm into A, that is maximum flux density into A. So already you know that what is the relation between that maximum flux and that is flux density and area. So the metal, the maximum flux is depends on that area of the metal and maximum flux density, and then we'll get that maximum flux. So this is the EMF equation represents that primary winding, and similarly we can write for secondary winding E2 is equals to 4.44 F pi f and N2. So this is the equation represents the secondary induced EMF. Now the transformer, when we can call as step up or step down, it is completely depends on that how many turns having in primary and secondary. Suppose if the number of turns in the primary is greater than N2, what we call the transformer step up or step down. When number of turns in the primary is greater than number of turns in the secondary, what we call the transformer step down transformer, right? Super. When n1 is less than n2, we can call it as step up transformer, right? So I think you cleared about the EMF equation, and now from this equation we need to be find that transformation ratio. So let's move on to the topic. And we are going to do some few problems on this EMF equation. Then only you can get clarity on this EMF equation, how to solve the EMF problems on EMF equation. So this is the most important problems you can get from third unit. Right. See, the transformation ratio, that is we can call as ratio of transformer. Here, the three important factors are we are going to discuss. One is voltage ratio, current ratio, volt and ratio. So these are the three parameters and three ratios we are going to discuss in the transformation ratio. So how we can write K in terms of voltage ratio? What is the K value in terms of voltage ratio? V1 by V2 or V2 by V1? So the transformation ratio, right? we can denote it by small k, and this we can represent in terms of voltage, that is given by V2 divided by V1. Now in terms of current ratio, how we can represent in terms of current ratio? Right, I1 by I2. Next, from this volt ampere ratio. So how we can write volt ampere ratio means K is equals to. So just cross multiply this one, V2 I2 and V1 I1. If you make this ratio, then you will get that volt ampere ratio. Now this transformation ratio finally we can obtain from this EMF equation. This equation represents that primary winding, right? What is the, so this equation is mainly obtained from that form factor. So what is the form factor here? How we can define the form factor? Right, the ratio between RMS value divided by average value, then you will get that form factor, and its value is 1.11. So this is the standard formula for form factor. Now we will see that how we can represent that equations. Right, so this is the equations, transformation ratio represent in terms of induced EMF and number of turns. So this is the equation represents the voltage and current. And finally, we can represent that in terms of kVA rating. If it is volt kVA rating means kilovolt amperes, right? If it is only volt amperes rating, we can represent V1 I1 equals to V2 I2. But here we are mentioning that kVA. Okay, so kVA kilovolt means, that's why we can represent that V1 I1 divided by 1000, V2 I2 divided by 1000. So generally kVA is the rating of power rating of transformer. So actually the power rating of motor and generator we can represent in terms of kilowatts. Why we can indicate the transformer power rating in terms of kVA? What is the way we can represent? So why we are using representation of power equation for that kVA rating? You can say answer in by voice. So because it will take time to type the answer. Why transformer rating represents in kVA? I already told you in your lab while doing the experiment. Why we are representing that transformer rating in kVA? Right, so I will tell you that. So kVA rating in the same, why transformer represents the kVA rating means, generally in a transformer we are facing the two types of losses, right? One is iron losses, another one is copper losses. Here iron losses is depends on that what type of material we are using. So iron losses is combination of eddy current and hysteresis, and copper losses is a depends on the load. Okay, now here the iron losses is depends on that what amount of voltage we are applying to the transformer. So when we apply the voltage to the transformer, due to this current will be flow, and this current makes that form a iron losses. So that's why the iron losses in the transformer should be depends on the voltage, and copper losses is depends on the current. Why? Because the copper losses is completely depends on the load. When we connected the load to the secondary, and it looks like a closed path. So when the circuit is closed path, then there is allowing of current, and the current is depends on that how much of load we are using. That's why if the load is increases, current also increases, finally we will get that copper losses. Already we have the formula, right, for copper losses, I square R. So that's why the losses happening in the transformer, one loss is due to the voltage, another loss is due to the current. That's why the transformer rating is represented in terms of kVA, kilovolt amperes. So that is the reason. So you may get for 2 marks question. So why the transformer rating represents in kVA rating? But in the case of motor and generator, the representation of power rating in kilowatts. Why? Because in these two devices, the energy should be convert. So you can converting from one form to another form. But in the case of transformer, you can't able to say converting. It is transferring from one level of voltage level to another level of voltage level. So that is the difference between that motor and generator and transformer. Right. So shall we do this one problem on this EMF equation? So just read this. I will read this question here. Right. See this example, the maximum flux density in the core of 240 by 2400 volts 50 Hz single phase transformer is 1 Weber per meter square. If the EMF per turn is 8 volts, determine primary and secondary turns area of the core. So how we can determine this value? EMF pattern is 8. So first of all, I'm going to write that what are the parameters mentioned in the problem. So the voltage level the given is 240 bar 2400. See, generally the voltage representation they given like this. One value divided by one value. So in this value, this numerator represents that primary voltage and denominator represents that secondary voltage. So they are always representing like this voltage levels. So the primary voltage V1 is equals to 240 and V2 equals to 2400. Right now from this equation we need to find that area of the core and primary and secondary turns, and what are the parameters that we have? F is equals to frequency, that is 50 Hz. See if the frequency they mentioned or not, didn't mention, so no problem. So frequency is constant for AC supply, that is 50 Hz frequency, and the flux, the maximum flux is given by 1 Weber per meter square. So these are the parameters that mentioned in the problem. Now we need to find that primary and secondary number of turns. Just write that EMF equation for primary. E1 is equal to 4.44 F 5M and N1. So this is the equation. Now from this EMF per turn equals to 4.44 F 5M. So they can represent in this equation. So finally, the number of turns in the voltage. So you can write N1 is equals to E1 divided by 4.44 F into pi F. So this is the equation for finding the N1. So here, how we can write the value of E1? So they given in the problem EMF per turn, right? So we have 240 volts in the primary voltage. So how we can write N1 is equals to 8 into 240 divided by 4.44 into 50 into 1. Find the value of this. Find the value of N1. See, we can find in another way. So just find that. I will tell you one more method. So generally, from the transformation ratio, we can write K is equals to V2 divided by V1 and N2 divided by N1, right? So here, what they given means, see, the voltage level is given by 2400 divided by 240. So that is 1 by 10. How we can write that? So this is the formula we can use. E1 is equals to, that is EMF per turn into N1, right? So from this, what is the E1 value? So here from here you can write E2 divided by E1. So from this equation you can represent that E1 is equals to V1, E2 equals to V2 from this transformation ratio, right? Now I am going to write this E1 is a V1, that is 240 equals to, what is the value of EMF per turn? 8, already they mentioned in the problem, and N1. So now from this equation we can write N1 is equals to 240 divided by 8. How much you will get? 3 is the 24 and 0, 30. So N1 is equals to 30. And similarly, for secondary induced EMF, E2 is equals to EMF per turn div into N2. And from this N2 we can write 2400 divided by 80. Sorry, only 80. Now we will get 300. Now finally we obtain that number of turns in the primary is 30 and number of turns in the secondary is 300. And what is the transformation ratio here from these two values? So here we know the value of N1 and N2. Then what is the value of transformation ratio? Right, 10, because 300 divided by 30. So the transformation ratio is 10 is to 1. Okay now, so 10 is to 1 in the sense it is a step down transformer. If it is 1 is to 10, then we can call it as step up transformer. So our first problem is over. Now we need to find the area. So for finding the area, we need to use this equation. right? So this is the equation we can write the phi m is equals to. So here maximum flux is given or not? Maximum flux density. Oh, this one. Okay. So they given the maximum flux density. Now from for finding the area of cross section, we can write E1 is equals to 4.44 F IM and N1. This is the equation for EMF induced in the primary. From this, you can write E1 is equal to 4.44 F. Instead of pi m, I can write Bm into A and N1. So we need to find the value of A, right? Now I can write A is equals to E1 divided by 4.44 into 50 into the maximum flux density. The maximum flux density is given by 1 and number of turns primary is 30. Now find the value of A. So here E1 is a 240. 240 divided by 4.44 into 50 into 1 into 30. Then find the value of A, area of cross section. What you will get area? Students, you got that value right? What is the value of A? 0.03. Then what is the units of area? So we'll check that value of A. Meters per. Super. So the value of A, we got that value here 0.03. So A is equals to 0.03 meter square. So this is the value of A. Now you may get questions like this based on that EMF equation. So we'll see that one more problem. Right. So this is the problem based on that EMF equation. Now we'll see that next topic is phasor diagram on transformer. So this is the most important topic. Oh. Right. So this is the next topic, that is phasor diagram of transformer. So before that, what is mean by phasor diagram? So phasor diagram in the sense, the phase angle between that, what is the voltage and current. So it means that if you consider the primary winding, so primary winding we have the primary voltage, and see, observe here, in primary winding we have input, that is primary voltage and primary current, so we can call it is no load current. Now how the no load current and voltage should be looks like, so what is the angle between these two? Okay now, so that is given by the phasor diagram. So generally I already told you that power factor is denoted by cos pi. So power factor is nothing but the phase angle between that voltage and current is called as power factor. Now this power factor is shows that what is the quality of the power we are getting. Suppose if you are getting the graph like this, so that is this is the current angle and it is the voltage. The angle between the voltage and current is 90 degrees, and this is the reference of phase angle. So here the angle, the power factor is nothing but the phase angle between voltage and current. Okay, now, so same thing we are going to establish here when transformer is on no load condition and when transformer is on load condition. So that is the thing we are going to discuss. Now, while solving this phasor diagram and while drawing the phasor diagram, we need to know that different parameters. What are the parameters means? V1, E1, and V2 is 0. Why? Because we are connecting on no load condition. So here it is open circuit. So there is no voltage drop across the load. That's why V2 equals to 0. And E2 is available here, and I0. So I0 is the combination of working component and magnetizing component, IC and IM. So already these two parameters we found in the OC and SC test. Okay, now let me see that how these parameters represents in the phasor diagram, that is graphical representation. So this is the graphical representation of these all parameters. Now if you observe this equation, if the graph, the voltage, the supply voltage and induced EMF both are in same phase. So same phase in the sense both in the same axis. Okay. So in this when it will obtain means when there is no load connecting on the transformer. If there is no load means so the power should not be waste. Okay. Now, so it is completely how much of voltage we are upping the input, the same voltage is available and storing on the device, because we are not connecting any load on the secondary. That's why at no load condition, the input voltage, that is primary voltage and primary induced EMF, both are in same phase. And here when the voltage is applied in the primary, the current tends to be flow. that current makes that flux generating in the core. So the dotted lines denoted by the flux, and we are taking the flux like this. This is the x-axis denoted by the flux. Now, if you reference that I naught here, this is the I naught, that is no load current, and the I naught is a combination of working component, that is the IC plus IM. So here are these two currents. One is working component, another one is core loss component. And the addition of these two, we can get that no load current. And in this condition, the angle between that voltage and current, that is pi naught. So this angle shows that phasor angle between the primary voltage and primary no load current. And if you see this diagram, the angle between the flux and induced EMF, it is 90 degrees. This is the phasor diagram represents that when your transformer is connected to no load, right? It means that the transformer is completely open circuited. So if it is open circuited means there is no flow of current, right? If there is no flow of current, we can't able to get voltage V2 here. So that's why we have only V1, I naught, E1 and E2. So here I naught is a combination of IC plus IM. So this is the phasor diagram of transformer on no load condition. So no load condition, you will get graph like this. Right. Now, if you observe if you connecting the load, see here, and this is the diagram represents that when we connected the load at the secondary, if you connected the load, then it makes a closed path. So when the circuit is closed, then there is allowing of current I2. Now we have the components V1, I naught, E1, E2, I2 and V2. So this is the parameters, and by using parameters we have to reference that phasor tag. Now if you observe this equation, see here, this is the pi x-axis. On x-axis you have to always reference the pi, and above the pi value you have to represent the V, and below you have to represent the E1. Now in this case, so there is the presence of I2 because we have connected the load on the secondary. So when we connect the load, then it makes a closed path, then there is allowing of current I2. Now this is the representation of I2, it is like this. Okay, now if you see this current in that, how it will be look like? Right. See, if you see this diagram here, I2 and I2 dash. So I2 and I2 dash means when the current is flow through the secondary circuit, it means that the load should needs more current than what we required previous. అంటే మనకి ఎప్పుడైతే సెకండరీ అనేది లోడ్ కనెక్ట్ చేసినప్పుడు ఎక్కువ కరెంట్ అవసరం అవుతుంది. That current is more than the no load current. That's why I am adding the current here. So this is, I require that additional current to supply the load, I naught plus I2 dash. Now if you observe this I naught, I2 dash and I2, it should be like this. So this is the I2 and it is the I2 dash. So both are in opposite but in the same phase. So how we can say in terms of words means I1, I2 dash and I2 both are in the same phase and in unequal magnitude. So one is having the negative parameter, another one is having the positive parameter. Why? Because this coordinate having that negative value and this coordinate having that positive value. And this is the representation of angles between that primary voltage and no load current. So no load current we can call as I naught. So from this you can write I1 is equals to I naught plus I2 dash because it is the primary current and it is the secondary current. Now we can represent here. And pi naught is the phase angle between that primary voltage and primary current, and pi 1 is the phase angle between that primary voltage and that is magnetic current. So this is the way of representing the phasor diagram when it is connected to the load. Now, if you want to get this phasor diagram, you need to assuming two conditions. One is there is no voltage drop in the winding, and secondary thing is equal number of primary and secondary turns. When it is happen means then you will get that E1 is equal to E2. Why? Because already we know the value of formula for transformation ratio, right? N2 is equal to N1 and E2 equals to E1. Now, when the primary number of turns and secondary number of turns both are equal, then you will get 1. E2 equals to E2 divided by E1, and finally you will get E2 is equals to E1. So when these two induced EMF are equal, then you will get the relation like this. E1 is equals to E2. So this is the two assumptions we need to be considered when the secondary is connected to the load. Next, so now we'll see that how many types of loads we have. So if you want to connect the load, it is always should be connected on the secondary, right? When the load is connected on the secondary, then there must be available of secondary current and secondary voltage. Generally, the loads are categorized into three types. So do you know that what are the three types of loads we have? What are the three types of loads we have? So I already told you in yesterday class, we have three types of load, right? So what are the three loads? What are the three types of load? So based on the load, we will categorize that power factor here. So right, resistive load. Then so just mention that letter. Right, super. So we have the three types of load: resistive load, inductive load, and capacitive load. Now, what is the difference between these three loads? Let me tell me that. Resistive load having that unity power factor, that is cos pi is equals to 1, and inductive load having that lagging power factor, and capacitive load we have leading power factor. So these are the three loads we are using in that secondary of the transformer. Generally, what we are using the devices in our homes, that all belong to the inductive loads. Now that's why when we are using the inductive loads, it consumes that electricity, then we are paying the current. If you are using the capacitive load, you don't want to pay money current bill. Why? Because the capacitive load is generating, so it should be generating that electricity. Okay. So now based on the power factor, based on the value of power factor, we can categorize these three loads. One is unity power factor load, that is resistive load, and inductive load called as lagging power factor, and capacitive load having that leading power factor. So leading, and how we can say that the leading and lagging means, if you use that resistive load, already you guys are studied in the network analysis, right? The resistive load, the characteristics of resistor should be linear. Linear in the sense, what amount of voltage is varying, the same amount of current will be varying. So here you are taking that I, and here you are taking the V. So it means that the current and voltage both are directly proportional, and these two parameters should be in the same phase. That's why the resistive load is always having that unity power factor. Now, why we call as inductive load as the lagging power factor means, here the phase and the current is lagging by that supply voltage. So that's why lagging by the supply voltage, in the sense, it means that voltage is constant, but the type of device we are using. So మనకు ఒక home లోకి వచ్చే voltage 230 volts, it is constant, but the same voltage is supplied to that TV, refrigerator, cooler, air conditioner like that. But voltage is constant, but the current dragged by this all devices should be different. So it means that the current is lags by that voltage. That's why the inductive load having that lagging power factor. Now, if we take the capacitive load, in that the current is leading the voltage. So leading the voltage means the current should be capable for every device we are using in this home. So that's why the capacitive load having that leading power factor. Now we will see that one more phasor diagram on this topic. Right. So this is the phasor diagram with unity power factor load. Unity power factor load in the sense we are using when we are using the resistor load. Okay now. So when we are using a resistor load, you are getting the phasor diagram like this. First, initially you had to draw the straight line like this, right? In that you had to reference that upper side E1 and downside E2, and it is equals to V2 and it is equals to V1. And x-axis you have to take consider that pi. When the current is flow to the secondary circuit, then the phasor diagram should be moves like this. So this is the part here. Now additionally we are getting this part, and this part is due to that when we are using the resistance load. So if you are getting this load, then you can form that right angle triangle with an angle of 90 degrees. Now if you are having the right angle triangle, how it will be means like it is a like see here. In that the base represents that resistance and the opposite side represents that reactance. Now, from this equation, from this right angle triangle, how we can represent the Z? So, what is the Pythagoras theorem? From the Pythagoras theorem, equals we can say that hypotenuse square is equals to adjacent square plus opposite square. So, you can write Z square is equals to R square plus X square. The same thing we are getting from here. So this is the total lines represents the hypotenuse, that is represented by Z1, and the opposite side of angle we can reference X1. The base we can represent the resistance. So IE1 R1, I1 X1, I1 Z1. So this is the value of impedance for primary. So Z1 is equal to I1 R1 plus I2 R I1 X2. So this is the only phasor diagram. Additionally, we are getting when we are using the unity power factor. And this is for primary winding and it is for secondary winding. I2, R2, I2, X2 and I2, U2. So this is see how we can represent that primary parameters and secondary parameter means if you represent the primary here, you can get opposite side. So like that you have to reference. So here you are referring the primary parameters, that is resistance, reactance and impedance. Quite opposite you are going to represent that secondary parameters, that is R2, X2 and Z2. So this is the phasor diagram we can get when we are using that unity power factor load. Let me see that one more phasor diagram. Right. So this is the diagram of when we are using that lagging power factor. So lagging power factor means see here. So this is our actual current, but when you are using the lagging power factor, your graph becomes like this. It means that it is lagging and it will decreasing. So lagging means తగ్గినట్టు అన్నమాట. So if you are using the lagging power factor load, actually you are having the current direction like this, but the phasor diagram should be comes to down. Okay now? So just this is the simple indication for that lagging power factor. Suppose if you using the leading power factor, this graph should come in this area, that is above the I2 axis. Okay now? If it is lagging factor, it is below the I2 axis. If it is unity power factor, it is on the I2 axis. Okay now? I2 axis పైన ఎప్పుడు ఉంటుందంటే UPF ఉన్నప్పుడు, unity power factor ఉన్నప్పుడు. Below the I2 axis you will get when it is lagging power factor. Above the I2 axis you can get when it is leading power factor. So I will show you that how it will be. Right. See here, this is the I2 axis, right? This is the I2 axis. Now, when we are using the leading power factor, then our phasor diagram should becomes like this. See here, this is the I2 axis, I2 above. So it means that the I2 is leading the voltage by phase angle phi. అంటే I2 అనేది supply voltage కి leading లో ఉంది. Okay na? So you can reference like this. Okay. So this is the phasor diagram for leading power factor circuit. So okay students, this is about different phasor diagram for transformer when we are connecting different loads. So already you guys are having that material, right? Just go through the material, then you can get the clarity. If you have any doubts, let me discuss in tomorrow class. Okay students, I'm going to end this class now. Thank you. In tomorrow class, we are going to discuss about equivalent circuit parameters of a single phase transformer. So I am going to end this class now. Thank you.